Namaste, welcome to my channel Pharma Knowledge Forum. In this session, I am going to discuss chiral separation of polar molecules using polysaccharide chiral stationary phase in reverse phase chiral mode. This is fifth session of chiral separation series. In this session, you will learn what is the procedure for selecting a stationary phase, what is the procedure for selecting mobile phase, what is the role of modifier in chiral separation, what should be pH of mobile phase for separation of isomers, what is the role of buffer on separation, what should be ratio of buffer and organic solvents, what is the effect of temperature on resolution, how separation can be improved. Polysaccharide chiral stationary phase. A polysaccharide is a large carbohydrate molecule. It contains many small sugar molecules that are joined chemically. Polysaccharide stationary phases are based upon chiral selector produced by derivatization of amylose or cellulose polymers. Amylose is a state chain polymer in which an alpha-1,4-glycosidic bond exists between D-glucose unit. This is a alpha-1,4-glycosidic bond. Cellulose is a state chain polymer in which a beta-1,4 ester bond exists between glucose monomers. This is the beta-1,4 ester bond. Polysaccharide chiral stationary phases can be classified into cellulose ester derivative, cellulose carbamate derivative, amylose ester derivative, amylose carbamate derivative. Following derivatives of above phases are highly used in both reverse phase chiral separation mode and normal phase chromatography chiral separation mode. Now question is, out of above phases, which one will be suitable for separation of polar molecules? I am going to explain the same in next slide. Stationary phase selection. Polar compounds can be classified into polar acidic compounds, polar basic compounds. Since compounds are polar, hence priority should be given to polar stationary phase while selecting the chiral stationary phase. Now question is, among these phases, which one is polar? Cellulose carbamate and amylose carbamate chiral stationary phases are relatively polar compared to other phases. Hence, amylose carbamate and cellulose carbamate should be preferable choice. Cellulose ester derivative can also be used with modifier. Now you are able to select the stationary phase. Now question is, how mobile phase can be selected? I am going to explain the same in next slide. Mobile phase selection. Mobile phase selection for acidic molecule. Mixture of water acidified with orthophosphoric acid or formic acid or acetic acid or trifluoroacetic acid and acetonitrile can be used, or mixture of 0.02 to 0.1 molar of potassium dihydrogen orthophosphate and acetonitrile can also be used. For basic molecules, mixture of 10 to 20 millimolar of dipotassium hydrogen orthophosphate or dipotassium hydrogen orthophosphate at pH 9 and acetonitrile can be used, or mixture of 10 to 20 millimolar of borate buffer at pH 9 and acetonitrile can also be used. For amine charged modifier like hexanoic acid or heptanoic acid is used at concentration 1 to 20 millimolar. Mobile phase selection for strong acid. Use 3 to 10 millimolar of sodium phosphate buffer at pH 7 as a base solvent and isopropyl alcohol as an organic solvent. Do fine tuning in mobile phase composition or change the modifier. Try to 1 to 5 millimolar of N,N-dimethyl octyl amine. During method development, one can make adjustment with ratio of base solvent and organic solvent. Use of alcohol as a modifier in the mobile phase will mask the stereoassociated sites due to hydrogen donor and acceptor properties. That is the reason acetonitrile is a preferable choice in reverse phase chromatography for chiral separation. Now you are able to select the stationary phase as well as the mobile phase. Now question is, what will be the ratio of aqueous solvent and organic solvent in mobile phase during method development? I am going to explain the same in next slide. During initial trial at the time of development, keep composition of aqueous phase and organic phase 60:40. Depending upon elution pattern of different isomers, ratio of aqueous phase and organic phase can be changed. Now question is how separation can be improved. Resolution is directly proportional to aqueous solvent. It means on increasing aqueous solvent, resolution is increased. Resolution is inversely proportional to organic solvent. It means on increasing organic solvent, resolution is decreased. Resolution is inversely proportional to flow rate. It means on increasing flow rate, resolution is decreased or vice versa. Resolution is directly proportional to column length. It means on increasing column length, resolution is increased and vice versa. Resolution is inversely proportional to sample concentration. It means on increasing sample concentration, resolution is decreased and vice versa. Resolution is inversely proportional to particle size. It means on increasing particle size, resolution is decreased and vice versa. Resolution is inversely proportional to injection volume. It means on increasing injection volume, separation is decreased and vice versa. Other factors are solvent polarity and its nature and column temperature. Now you are able to select the stationary phase, mobile phase and its composition. You are also able to increase the resolution between different isomers. Now question is whether it will work or not. I am going to explain the same taking different acidic and basic molecules. Case study basic molecules. This is the 1,2-diphenylamine. This molecule having only one chiral center and hence this molecule will have 2 to the power 1, that is the 2, means this molecule will have 2 isomers. Now question is how both isomers can be separated. Since molecule is a polar, hence preferable stationary phase will be amylose carbamate or cellulose carbamate. Preferable pH of aqueous phase will be basic. Organic component will be acetonitrile. Flow rate can be kept 0.5 ml per minute. Ratio of the aqueous phase and organic phase can be keep initially 60:40. Now see in which chromatographic condition both isomers are getting separated. Column amylose carbamate, particle size 5 micron, mobile phase borate buffer and acetonitrile in ratio of 60:40, flow rate 0.5 ml per minute. Retention time of both isomers are 15 minutes and 17 minutes. Both isomers are well separated. There is base to base separation. Case study to acidic molecules. Mandelic acid methyl ester. This is the acidic polar molecule. This molecule having one chiral center. Hence, this molecule will have 2 to the power 1, that is the 2 isomer. Now question is how both isomers of this molecule will be separated. It means what will be stationary phase, what will be mobile phase, what will be pH of the mobile phase, what will be the ratio of aqueous and organic solvent, what will be flow rate, what will be column temperature. As molecule is a polar, acidic and hence preferable stationary phase is cellulose carbamate or amylose carbamate. Compound is acidic and hence pH of the aqueous phase will be acidic. Initial ratio of the aqueous phase and mobile phase will be kept 60 to 40 and depending upon the elution pattern composition can be changed. Now see in which chromatographic condition both isomers of these molecules are getting separated. Column is cellulose carbamate, particle size 5 micron, mobile phase is acidic formic acid and acetonitrile in a ratio of 60 and 50. Flow rate is 0.5 ml per minute. Column temperature is 25 degree. Both isomers are getting separated. That is all about this session. Write at least one of your learnings in the comment section. I am on a mission to train more and more pharma professionals by sharing my skill-based knowledge. But if you join my channel, then only I can help you. Subscribe and hit the bell to see a new lecture on each Sunday. Let us see you in my next session.